So, welcome back. So, this is first law of thermodynamics. So, we're going to talk about a few things today. We're going to talk about heat and internal energy. Heat, of course, is energy in transition. It's internal energy when it's inside the first object. It's internal energy when it's inside the second object. And it's heat when it's been transferred. And then we're going to use that. And we're going to do a whole series of things about calorimetry. And then we're going to talk about the first law of thermodynamics, which is work and heat combined together. And then we're going to talk about heat transfer mechanisms, which are conduction, convection, and radiation. So there's actually a lot of work in this chapter. This is the sort of the books tend to have some chapters there's not so much in, and other chapters there's more in. It's just the way it goes. So let's talk about heat and internal energy. So a couple of definitions. Internal energy is all the energy of a system, if you like, an object, that is associated with its atoms and molecules. It's not, if I take an object and I throw it across the room, its translational velocity changes its mechanical energy. It has a half mv squared because of its motion. But it isn't changing its internal energy. Its internal energy is all about the vibration of the molecules in terms of a solid. So just because I throw this thing across the room does not mean to say while it is traveling that it has more thermal energy. It doesn't. It has more mechanical energy. So we're drawing a distinction between thermal energies or internal energies and mechanical energies. And when it hits the wall at the other side, then that mechanical energy gets changed into heat, basically. So it eventually becomes internal energy, but not just because it's moving while it's moving. So we've got two columns. One is mechanical energy column, and the other one is the thermal energy column. All the energy associated with the atoms and molecules, when viewed from the reference frame at rest with respect to the object. So when the object's moving, my reference frame moves, so I don't care about that motion. I care about the vibration of the molecules. A sample's temperature is directly related to its internal energy. That's a really, so there's a whole series of like insights that came to me as I struggled with this section in the course, where it was like, man, I wish they'd made that much clearer, you know. Now I get it. It ties it up an awful lot of things. And so it's not that temperature equals the internal energy. Numerically, they're not equal to each other. But if I increase my temperature, I have increased my internal energy, or my thermal energy. The terms are interchangeable. If I double my temperature in Kelvin, I have doubled my internal energy. So they are not equal numerically, but they go hand in hand. And if you have an increase in temperature, you must have had an increase in internal energy. And if you have an increase in internal energy, there must be an increase in temperature. There's no other way around it. It's kind of like, you know. So I didn't get that for the longest time. And so there were clues in the question that I just was missing. And then heat. Heat is the transfer of energy across a boundary of a system between one object and another, basically, due to the temperature difference between the system and its surroundings. So heat is driven by temperature changes. So no temperature change, no heat transfer. If there's heat transfer, there must be temperature change. And then work. Work is the transfer of energy across a boundary due to mechanical manipulation such as compression and expansion. So we're bringing in work, and that's basically was what basically Joule was able to do. That was his great thing. Before that, they thought that heat was completely, heat and internal energy were completely separate from mechanical energy. And they talked about this caloric fluid and all this kind of stuff. And then Joule, on his honeymoon, went to the Alps, and him and his wife were measuring the water temperature at the top of a waterfall and the water temperature at the bottom of the waterfall. And they were looking at the temperature change difference and relating that to the height of the waterfall and the work done by when the water falls. And And so I realized, oh, it's the same thing. It's what you get mechanically is converted into, what you lose mechanically is converted into a temperature effect, a thermal effect. So now we're going to link work and heat. And from a kind of, in a way, a philosophical point of view, the link between work and heat, the link that takes work to heat is friction. And if you just take your hands and just rub your hands together, you can feel that. You know, you rub your hands together and your hands get warm because you're changing mechanical energy into thermal energy. And the kind of philosophically significant bit is it's very hard to go back the other way. You can take machines to some extent, and you can take chemical energy, say, and you can make it into thermal energy and then use that thermal energy to drive a motor, and you get mechanical out. But you've got to work really hard to do that. By and large, it's a lot easier to do work into heat, whether you like it or not. You know? And one of the issues is that the more and more the mechanical universe is mechanical, the more it does stuff, the more that energy, which is in localized bits, the sun, you know, the earth, all that, the temperatures degrade, and you end up with a uniform amount of vibration all over the universe. And there's not much you can do with it. We need localized sources of energy. So we're going to bring work into the equation, literally into the equation. Okay, so the SI unit for heat is the joule, because it's just energy. Traditional unit for heat is the calorie. Remember that? The calorie, which is the amount of heat needed to raise the temperature of 1 gram of water by 1 degree C, from 14.5, to be want to be specific, to 15.5 degrees C. The energy content of food is often measured in calories, big C rather than little c, which is the kilocalorie. I'm always a bit cynical. And, you know, anybody know how many calories are in a Snickers bar? I know, actually, pretty closely. It's 242, I think. Last time I looked, anyway. Calories. And so, 242, you know, that's okay. It's really 242,000 calories. And even that would make me kind of pause, you know. A huge amount of energy is in food. A huge amount. In fact, you know, again, waxing a bit philosophically here, when on the Fertile Crescent, basically, you know, the Middle East going eastwards, the big input was the cultivation of grasses into grains. And so we stopped being hunter-gatherers and we started being farmers to that extent. And because of the caloric yield of these grasses, were just great. When you're a hunter-gatherer, you spend all your time hunting and gathering. You know, you don't have time to develop math and culture and the like. You're feeding yourself. And when you get a real rich source of calories, you can have a meal, 3 meals a day, and you're kind of like satisfied. What are you going to do the rest of your time? Well, have kids, develop math. I mean, it's like, boom, population grows, culture grows, economy grows. You get rich and powerful and strong, and it goes on. And the wonderful thing about the Fertile Crescent is that it kind of goes east to west. And so it turns out that what works in one part of the Fertile Crescent will tend to work in the next, and tend to work in the next, and tend to work in the next, because it's at the same latitude. And so you got this innovation spreading through, you know, the known world quite dramatically. And that's just happenstance. Then you can start, you know, developing grasses that work further north and developing grasses that work further south and all that kind of stuff. But it's amazing. Food is just, it's amazing. And also, I got to tell you, I mean, I'm an ex-vegetarian. I was vegetarian, and all I did was ate bread. And there comes a point when you need protein, but I was filling up on bread, and it was not good. And so I decided that if I couldn't be a good vegetarian, I was going to go back, and I won't eat. I don't eat red meat, but I will eat chicken on occasions. Also, my family's not vegetarian, so I was cooking for them and cooking for me, and it was a real pain. And I got to say that although meat tastes great, it's highly inefficient, because that poor animal eats the grain, which we could have eaten, and then it produces protein, which then we eat. So it's going through a middle animal, and that's not efficient. So we'd be much more efficient, actually, if we not that I'm preaching to you, but if we became vegetarian, we'd be much more efficient. And in fact, one of the ironies is that as the developing world is becoming developed, they're developing tastes for meat. Well, I understand it's really tasty, but ironically, it means that we are using even more energy than we would be if it was a vegetarian issue. So think about it. Vegetarianism, there's no chickens in the corner, kind of like running away from you. I mean, if we had to catch our own food and kill it, I think there'd be a lot more vegetarians in the world, because I couldn't do it. I've fished, and I always put them back. I cannot eat the fish. I look at it, it looks at me, it can't. Okay, back you go. So food has a lot of energy in it. And also you'll find things like the British thermal unit. British thermal unit is it's the amount of energy required to raise 1 pound of water, or maybe 1 ounce of water from 1 by 1 degree F, basically. It's the same principle. We have conversion factors. You don't have to know the conversion factors. I will give you them. You need to know that a calorie is, 1 big food calorie is 1,000 little calories. I want you to know that. But you don't need to know that BTU is 252 calories, and you don't need to know 1 calorie equals 4.186 joules. But I do like to ask energy conversions on this, so brush up on your factor label stuff, because it's a nice time to just go back and review that. Which is the smallest unit? Let's have a look. BTU calorie. So let's see if we can get some sense of this. Oh, look, calories in everything. So let's have a look. We have a calorie, and let's have a look. 1 cal equals 1,000 little cals. And 1 BTU equals 252 little cals. And 1 joule equals 1 over 4.186 calories. Yeah, 1 calorie equals that, so 1 of that equals 1 over that. So which is the smallest unit? Well, it goes from big to small. It goes calorie is bigger than BTU, is bigger than the cal, is bigger than the joule. The joule is smaller than the calorie. So joule is the smallest unit. Can somebody give me a visualization of what a joule is? If I said, demonstrate to me a joule of work being done with everyday objects, what would you do? If I said to you, demonstrate to me a Newton of weight with everyday objects. Hopefully these are part of your everyday life. Hopefully they're not something you only see when you go to your mum's house. On the dining room table. Apple, yeah. So Newton is an apple. Newton's apple, Newton's an apple. What's a joule in terms of newtons and distances? A meter, yeah. And what's a typical meter? 36 inches, basically desk height. So pick an apple up from the floor and put it on the table, that's a joule. Okay? So inside my Snickers bar, 242 cal, which equals 242 little cal, which equals 1 little cal, which equals 4 times 242 joules. You know, that's like picking, did I do that right? Yes, I did. Did I do that? Oh no, 42,000. I did not do that right. That's like 250,000. We've got 4 of them. So inside that Snickers bar is like picking up 1,000,000 apples and putting them on a desk. That's a lot of work. That's a tremendous amount of work inside that chocolate confectionery. You know, so tremendous energy in those things. Use factor label method to convert 17 BTU into joules. So we have 17 BTU, but I don't want BTU. I want joules at the end. So let's plot out where I can go. I can go BTU to calories, and then calories to joules. I don't need to do that one. I can just go it by Rex. So then I go, okay, BTU on the bottom and little calories on the top. That's 1 BTU equals 252. That got rid of my BTUs. Remember this good old factor label? And then I have calories, and I want to go to joules, so I'll put calories on the bottom. So 1 calorie is 4.186. So I come along and I go 17 times 252 times 4.186 is equal to, wow, this is 17932.8, and it's going to be joules. So that's 17,000 joules and about 17 BTU. Okay. The 2 goes to 3, so that's that one down there. Yeah. Yeah. So it's a good chance for me to just double check. Do you still remember the factor label technique? I'll give you all the conversions. It's not that you need the conversions. Oh, so this is actually very... So when I met my wife, did I tell you this? When I met my wife, I was like 37. I was 47. 45, I think I was. 99, 45. And there's sort of, so you might not have realized it yet, but there's like these plateaus in your life. There's like the teenage to, you know, young adult, you know, the teenage to early 20s, and then there's a bit of a step, and then there's, you can tell somebody around their 30s, you can tell them from early 20s, and then there's like 40s and so on. And these transitions happen really kind of quickly. For me, my experience was, you know, a month, and I was like, man, I was older, you know, just like it suddenly... It just all happened at once. And I met my wife kind of like there. And we got married. And then within a month, I was like here. And she was saying to me, she goes, you know, I've noticed that, you know, you seem to be getting a little bit heavy. And I said, it's your cooking, sweetie. It's great. So she said, maybe it's time we join the Y. Or, no need. I said, no need. I said, I got a plan. I said, you know how we go for lunch every day? Because we both worked at USF, we'd have lunch every day. You know how we go for lunch every day? And you know how you're on the 4th floor of the Communication Science and Disorders building? I'm just not going to take the lift anymore. You know, my wife's really smart, and you know, she kind of says, let's do the math. So let's do the math, okay? So you have an 80-kilogram person, so here's a person, and they're going to climb, so they work off a Snickers bar. Because I was having she found Snickers bars in my pocket every day. So I'm going to climb. How high do I have to climb to work off the Snickers bar? Well, let's have a look. I'm going to be 800 newtons. So that means my lifting force would equal 800 newtons. Remember that from mechanics? It's just, you know, my weight down equals what I have to lift upwards to. I'm not accelerating, I'm just like, you know. Okay, so I'm going to say the work done is equal to my force times my distance times the cosine of the angle between. Well, the cosine of the angle between is going to be, it's going to be 800 times the distance is what I want, times the cosine of the angle. Well, they're both in line. So it's going to be 1, which equals 800h. And what does this equal? Well, let's have a look. I said 250 food calories. So let's just work this out. I want to go from food calories to, let's go back. I want to go from food calories to joules. So I want to go, first of all, from food calories to calories. That's 1 calorie is 1,000 little calories. And then I want to go from calories to joules. So it's 1 little calorie equals 4.186. So I have little calorie down here. I have 4.186. So cancel, 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 cancel. Put in my joules. So I'm going to get 250 times 1,000 times 4.186 is equal to, oh my word, 1046500. That's 1,000,000 joules. Okay? 1,000,000 joules. So, okay, my 1,465, that's how many joules I got to work off. And I'm going to work it off at 800 times h. So that equals 1046500 over 800. Actually, divided by 800. I think I'm going to get away with that, yes. 1308.125 meters. Which is, well, let's say that there are 4 meters, 12 feet, about to 5 meters. Let's say there's 5 meters to a floor, 15 feet between floors, like in a office building. You know, they don't have 10-foot ceilings. They have, let's say 15. Let's be generous, 15 feet. So let's divide. That by 5. Divided by 5 equals. That's going to be 261 stories. You know, floors. My wife's on the 4th floor. I would have to do this, oh man, what? Yeah, just a phenomenal number of times. So my get fit exercise was not going to work. The trick was, don't eat Snickers bar, you know? It's kind of like that. Now, actually, just by the by, I was at a party and I met this older gentleman, he's probably like 50. And he was the boxing coach at a gym where one of my buddies goes. And so I said, what got you into, you know, training boxing? And he said, I was the middleweight champion of the world. I know, welterweight or something like that. He wasn't heavyweight, he was. I said, what? And he goes, I was world champion boxer. And I looked him up, and he was a world champion boxer. And so I was talking to him, you know, about staying fit, because the guy looked amazing. And I said, so it was kind of crazy. How do you watch your weight then? And he goes, it is diet and exercise. It's not one or the others. You know, if I don't exercise, then I don't do as well. But if I just exercise and eat badly, I got to work really hard. It still doesn't work. So he goes, you know, no processed food, all the stuff you know, no processed food, and you exercise every day. So I'm not doing either, but you know, I got it written down on my calendar. Actually, I just had, sorry. So, and they said that for a person my age, I was actually in pretty good shape, which is kind of nice. Temperature versus heat relationship. So, if you take a substance like water, but it could be aluminum, it could be anything, and you start heating it up, then there's a very common pattern you start off and you heat up the solid, and then it starts to melt. You're still putting energy in, and it starts to melt. And then when it's all liquid and you heat it up, it gets hotter and hotter liquid, and then it starts to vaporize. The big thing you notice is the boiling, but that's vigorous vaporization. And then when it's all vaporized, if you could capture it, you could heat up the vapor and you can get vapor that's hotter than, you can get steam that's hotter than steam. You know, and you've got to watch out for that in things like turbines and turbines, they'll use high pressure superheated steam. And that's really energetic. So it turns out that not every material does this. Some things sublime, which means they go from the solid that's heated up, they go to, they go to the vapor. I should really go to that. They go to the vapor. That's sublimation. Not many things do that at atmospheric pressure, but some do. And it turns out if you take other substances that follow this pattern and you mess with the pressure, you can get them to sublime. So, and I guess things like dry ice will not go to liquid. It goes from the solid CO2 to the vapor CO2, the gas CO2. So something sublime. So this is a common pattern, but it's not the universal pattern. Okay. But this pattern is important because typically we are working with things that will do this. So I'll work with ice or oil and water and stuff like that. And what you find is you get solid ice will then reach its melting point and melt. And then once it's all melted, the water will go to its boiling point, and then it will vaporize. And you regard it as doing it uniformly because it makes the math easier. So you don't let one bit melt while the other bit, it all. Now what happens here? If I got to pay for this melting. When I was a student, I thought that if you started and got a little bit of melted ice, it would inevitably melt. It was like a contagion, you know. A little bit of melting would dismantle all the solid. And I think I got that from the idea of candle wax, where it just seemed like as soon as one bit melted, it all inevitably melted. But I wasn't thinking too clearly, because if I took the flame away, it stopped melting. Yeah. So it turns out that if I put enough energy in to raise my solid, say the ice, to its melting point, and then I put enough energy in to only halfway get across this plateau and stop. So I have it in an insulated can, and I stop. And then I look in. I would see half ice, half water. And if I put the lid back on, perfect insulating can, and I came back 2 weeks later, half ice, half water. It doesn't all become half melted. There is two phases. There is the icy phase and the water phase. And if I measured the temperature, they would have exactly the same temperature. And I always thought, well, ice must be a little bit colder than, any ice must be a little bit colder than any water. And it's not true. They can be exactly the same temperature. One is in the ice state and one is in the water state. It's just it takes energy to break those solid bonds. And if you haven't paid for that, they don't get broken. So it's not that this liquidization is a contagion. It's just you got to pay for it. We tend to well, let me ask you a question. So, who's Thoreau? Anybody know who Thoreau is? Yeah, Walden Pond. Yeah. So Thoreau was this poet, really, philosopher, who maybe 200 years ago, 150 years ago, lived in Boston. decided to decide what it was like as a simple life. And so he went into the woods around Walden Pond, which is in the suburbs of Boston now. And he built himself a shack. And he decided to live there, living off the land. So he'd hunt and he'd try and grow some food and all this kind of stuff, but living off the land. And he wrote a book about it, Walden Pond. It's kind of interesting read. I got mixed feelings personally. It kind of like, I get the impression it's kind of like somebody who's well-to-do deciding to live off food stamps for a while and see what it's like. But it turned out he went home to see his mom every now and then. So he wasn't really living off the land for like 2 years. He was, not all the time. That's what I heard anyway. And he describes how, people were friendly, people would help him, which was kind of nice. And he learned the tricks, and he got better as time passed, But there was always had this issue about, it was some rich kid who was playing at bin Paul for a while, But he describes how in the winter there's not a heck of a lot to do. You can't grow crops, and there's not much to eat. There's some game in New England, but not that much. So spend a lot of time inside. And he noticed that on Walden Pond there was the ice company was chipping and sawing away at the ice. And he said he found it fascinating to realize that the ice from his pond would find its way to cool the drink of, and he said somebody, and he mentioned, well, he didn't mention where they were, but he mentioned somebody from a society that I found quite shocking. How far away do you think you could transport ice in, 150, 200, before steam locomotives and all that? How far do you think you could transport ice before it melted in the winter time? Could it go to California? Could it go to, Well, that's what I'm saying. Taking all that into account, how far do you think it could go? It's winter time in New England. How far do you think it could go?
Easy 20 miles or more.
Okay, yeah, 20 miles. Anybody? Come on, let's get some.
50 miles.
50 miles, yeah? 200, yeah. How would you transport it? Boat? I mean, Boston's on the harbour, so you could take it down the coast and all that kind of stuff. Yeah. India. It was imagined it had been dropped into some Maharaja's drink, that's what he said. And it's like, yeah, you've got to be rich, that's for sure. But India. And what they do is they take this ice and they'd pack it in sawdust. And they'd put it in crates. And they'd just put it on boats and they'd send it. And it was such a good insulator. The sawdust with the air trapped inside and the crates. And it was so massive, a piece of ice. Remember our dimensional analysis, the bigger the piece of the ice, the less the surface area is for a given volume. So if you have a huge piece of ice, it melts proportionately slower than take that same volume and break it up into a whole bunch of cubes. That's why crushed ice melts quicker in your drink than cube ice. You get the same amount of ice, it's just different surface area. So keep it in big blocks, insulate it well, you can ship it around the world. So I read that and I thought, after a while I was thinking, hold on, that's Thoreau. What does he know about that? Didn't follow it. So I checked, and it turned out there was a company that was, this guy made a fortune shipping ice around the world on boats, New England ice around the world on boats. And what put him out of business was steam, because a rival company got the steam ships before he did. And so they could deliver it faster and cheaper and more reliably. And that put him out of business. And then he came back, he bought himself a steam ship and came back and made a second fortune. And the final thing that put him out of business was the ammonia refrigeration, the ice houses, where they started building them in the hot climates where people didn't own refrigerators, but there'd be an ice house in your town that made ice using ammonia, I guess, and you could you could buy ice from there. So, okay, so this is a very important diagram. I'm not above asking you to reproduce it, so make sure you know. These slopey bits represent increasing temperature with heat, and the horizontal bits represent no increase in temperature with heat. You're melting or you're vaporizing. You do one or the other. You change the temperature or you melt or vaporize, yeah? And the width of this is, the only thing that's wrong about this diagram is it actually looks like that. If you want to store energy, don't take a solid and heat it up. Take a solid and melt it. Take a liquid and vaporize it. Because thermodynamically, what you use to make it change phase, you get back if you do things right. So you can store much more energy by changing the phase of something than you can by changing the temperature of something. So, and that's how our refrigerators work, for example. Air conditioning systems work. So segments A, C, and E depend upon the respective specific heats. We'll talk about specific heat. And sections B and D depend upon latent heats. So we got specific heats and latent heats. What's a specific heat? Worry about this side of it. Different materials require different amounts of energy to change temperature. They don't all heat up at the same amount. Aluminum heats up quite readily, changes its temperature with only a little bit of heat, whereas concrete or wood or something takes a lot of energy to change the temperature of a slab of concrete or a piece of wood. Water is actually incredibly hard to change the temperature of. Incredibly hard. So we need some figure of merit which will characterize how much energy we need per mass to raise the temperature by 1 degree. Well, what kind of mass, what kind of temperature? So you get different units. We can talk about the energy per kilogram Kelvin, the energy per kilogram degree C. They're the same because the size of a Kelvin is the same as the size of a degree C. But we can talk about, calories per gram per degree C. Lots of units are out there. Little c is the specific heat. It's to do with the material. We can look it up in a book. And it is Q over M delta T. It's the amount of energy, the heat, divided by the mass, divided by the temperature change. That's how we find our unit for specific heat. Specific heat is like density. It's to do with the substance. Heat capacity is like mass. It's to do with the sample. So the heat capacity is not the heat per kilogram per degree C, it's the heat of the object per degree C. So it's heat per degree C. We don't tend to talk so much in terms of that. We tend to use this much more often. But no, the other one is there, and don't get caught out by that. Let's work one out. What is the specific heat capacity of a gold if it takes 3096 joules, that's my Q, to raise the temperature of my M is 4 kilograms, by my delta T equals 6 degrees C. So I say C is equal to Q over M delta T, so C is equal to 3096 over 4 times 6, which equals 30.96 over 24. So C is equal to 3096 divided by 24, which equals 129. joules per kilogram degree C. What can I do to make this a bit more interesting? I could give you a final temperature and initial temperature, so you're not, which one are you going to use? You've got to use the difference between them. I suppose I could give you in non-standard units and make you do some conversions, but in essence it's simple enough, yeah? I suppose I could ask you to plot me a graph of C versus delta T for a given material. You know, you get inverse or something, you know. You can do all those things. Let's think conceptually. Consider putting a 1 kilogram sample of a high specific heat material, let's say concrete, and a 1 kilogram sample of a low specific heat material, let's say aluminum, so we can visualize it, in an oven. So it's in the oven. Both materials start at the same temperature, room temperature, and end at the oven temperature. So you put them in, and you wait for as long as it takes until both of them are at the oven temperature. Which material will heat up fastest? Well, the high specific heat, they're both going to go through the same temperature change, yeah? Do they both have the same amount of energy requirement? No. Which requires more energy to change its temperature by 1 degree C? Is it a high specific heat material or a low specific heat material? High. Concrete takes more energy to heat up by 1 degree than aluminum does. So, they're both getting the same amount of energy in the same amount of time because they're both in the same environment. So you can say, oh yeah, that's going to heat up fastest because it's going to get its temperature, it's going to get its energy real quick. And this one, not so fast. So it would be the low specific heat material heats up fastest. It takes less energy to heat it up. So it's going to get it sooner. Agreed? Which material will require more heat to reach its final temperature? Well, the whole point about that was that the high specific heat material takes more energy. So that requires more heat. Here's the kicker, which will store more energy because of the temperature change. Concrete. So that informs us as far as an awful lot of technology is concerned. You want to use a cooking pot, best to make it out of a metal like aluminum, because it will reach a higher temperature sooner. You make it out of concrete, you'll be spending a lot of time heating up the concrete before you heat up the food inside. So, be wary of making a home out of metal, because with a bit of sunlight it's going to get hot, and that means you're going to be uncomfortable. Make a home, if you can, out of concrete. Why? Because during the day it takes a lot of thermal energy to raise its temperature so that it warms up gradually during the day and doesn't get too hot. And then at night it takes a long time to give up that energy, so it stays warm. Your metal home will be boiling hot during the day and freezing at night. Not so much in Florida because we're in a humid environment, but in the mountains, say, of Colorado. Stone home will be nice and cool during the day and actually nice and warm during night. So it stabilizes the temperature. My grandmother's generation did not have refrigerators. They'd go to the shops more frequently. It's true. My grandmother would go to the shops maybe 3 times a week. She didn't do weekly shopping. She did, a couple of days. But she would buy butter and she would buy milk. And she had what was called a larder. And the larder was like a closet. And the significant thing about the larder, if you walked into the larder, the thing you would notice was there was a huge stone shelf. There were other wooden shelves, but there was this huge, thick stone shelf. And that's where she put her milk and eggs. Whatever she wanted to keep at a nice, cool temperature, she put on that stone shelf. Because it wasn't heated up or much more stable temperature and relatively cool temperature. And I remember the big innovation was she found, so my grandmother, so it's generational differences. Maybe you've noticed it in your family. My grandparents seemed relatively well off because they'd got rid of the kids. My parents seemed real poor. It's all because of me and my brother when you think about it. And my granddad was, he was a cooper. He made barrels. It was the end of his career. He basically worked in business, worked in barrel making for 40 years. At least 30 years when I was a kid. In those days, he worked for one employer all his life. And not uncommonly. And those days, as you stayed longer, you got paid more. It was, you've got years more experience, more money. Wasn't rich, lived in government housing, but over his lifetime was able to support 3 kids on one income. Couldn't do that today. I couldn't do that today. And the big innovation was, because I noticed my grandma got all the gizmos before anybody else did. The big innovation was there was this weird kind of paper-like container. It was shaped like 2 milk bottles put side by side, very light, and it was polystyrene. It was like the first time I'd seen polystyrene. And you took it out and you put the 2 milk bottles in when they were cold and you put them on and it insulated them. That was like, oh, my grandmother raved about this. That was before refrigerators came in. It wasn't that there were no refrigerators, but my family couldn't afford a refrigerator. So making sensible use, careful use of materials properties. All right, so we know how to characterize. So we know how to characterize temperature changes. What about melting or vaporization? There's a thing called latent heat. There's 2 of them. There's the latent heat of, it's sometimes called latent heat of crystallization. I've seen it called latent heat of liquefaction, but crystallization is commonly used. That's going from solid to liquid or back, liquid to solid. And then there's the latent heat of vaporization, and that is vaporization, and that is going from liquid to vapor and back. And it's just the heat divided by the mass in both cases. What is the latent heat crystallization of solid gold? I think these are real numbers, but let's have a look. So my Q is equal to 20100 joules, and my mass is equal to 300 grams, which equals 0.3 kilograms. So my L, which is equal to Q over M, is equal to 20100 over 0.3. So L is equal to, let's have a look at that, 20100 divided by 0.3 equals 67,000. So this is 67,000 joules per kilogram. That's that guy. Let's start putting it together. There are 3 classic examples of calorimetry. The first, you have a hot thing and a cold thing, and they don't mix together, and the solid thing stays solid and the liquid thing stays liquid. And the next thing is we have a cold thing, let's call it ice, and a hot thing, let's call it water. And the ice melts and becomes water. And then the third kind of thing is, we have a solid thing, let's call it butter, and a liquid thing, let's call it oil. And the butter does melt, but it does not become oil. So we have these two liquids that are not the same. Those are our three possibilities. So let's go through. An isolated system, so we need some kind of cup with a lid. The heat lost by one element is equal to the heat gained by the other element. No heat escapes, no heat gets in. Consider adding a hot solid to a cold liquid. So here's the first example. 4 kilogram, 20 degrees C sphere. Specific heat equals 8 joules per kilogram degree C. Is dropped into a calorimeter containing 6 kilograms of 10 degrees C fluid with a specific heat of 4 joules per kilogram degree C. There's no change of phase. That means the solid stays solid, the liquid stays liquid. What's the equilibrium temperature? So I end up with this inside there, and it's all at the same temperature. Q, delta Q equals 0. Now you might have learned, and I've said previously, Q lost equals Q gained, but I prefer mathematically to say the change in heat equals 0. Because for the whole system, yeah? So I say, well, let's look at this solid. The mass of the sphere times the specific heat of the sphere times the temperature change of the sphere. It's only changing its temperature, it's not melting. So no latent heat. Plus, let's look down here. The mass of the liquid times the specific heat of the liquid times the temperature change of the liquid is equal to 0. Let's put our numbers in. I'm looking at my diagram. 4 times 8 times 20. Oh no, sorry. Bad me. Temperature change. Temperature change is T final minus T initial. And this is for the sphere. In fact, let's going to back off a little bit. I jumped to the numbers too quick. Plus the mass of the liquid, specific heat liquid, temperature final minus temperature initial for the liquid equals 0. So now we can put numbers in. 4 times 8. Now, I don't know what the final temperature is, do I? So let's just leave it as T final. Oh, I've got to end this soon. Okay, I don't know what the final temperature is, but I do know my initial temperature is 20. Yep. Plus the mass of that is 6. Plus the specific heat is 4. I don't know what the final temperature is, but I know its initial temperature was 10 equals 0. Now, conceptually, I know that T final equals T final. So 4 8s are 32, 32 TF minus 640 plus 6 4s are 24, 24 TF minus 240 equals 0. Add your TFs together. 56 TF is going to equal, add your temperatures together, that's going to be 880. Take it to the other side. 880. So TF is equal to 880 over 56, which equals 880 divided by 56 equals 15.7 degrees C. So not bad. It's one of the simpler examples, but it's not bad. Okay. I'm going to just pause that here. I'll stop it actually.